Excellent. Well, good afternoon, everybody. My name is Gene Swick, WB9COY, and I'm involved with the Arizona Near Space Research group in the Phoenix area. Kind of an interesting story how I got involved with that group, since I live in California now, in the San Diego area. My son goes to Arizona State, and we were actually attending a rugby meet at the facility that Jack is at, the lead of Arizona Near Space. And I saw open house, and I saw ham radio antenna, and I had to figure it out. So I roamed around, tracked out where that coax led to, and there was Jack from Arizona Near Space. We talked for a while and found out that he's heavily involved with balloon launches and also CubeSats. That was a perfect match. So the stuff I do for hobby lately with programs like, I've created a program called Snapsat, which we'll see later on. That's kind of marrying the processor that's in your phones, called the Snapdragon processor, with the satellite project, CubeSat. Jack and I have participated with launching Snapsat payloads for the University of Texas for about 3 times now, and we'll talk about that a little later on. So this is the organization. Jack said, say a little bit about us, and I accommodated that. So mission statement for that organization, heavily involved with STEM, promoting science, technology, mathematics through amateur radio and high altitude weather balloons. And he's also involved with the NASA Space Grant Program, Ascend, and he's been involved with that since 2001. So a little background, Jack founded the organization. His call sign is W7JLC, and he's successfully launched over 91 missions to date. Jack centers around amateur radio experimentation and also safety. So all the balloons are actually launched with hydrogen now. Helium is almost like unobtainium. The last launch we did from the Yuma Hamfest about 2 years ago, I think the tanks almost cost us $600 to get it launched. So hydrogen is just, helium is no longer part of our payloads anymore. It's all hydrogen. So there's safety that goes along with it. And you'll see some shots later on of how Jack manages that. So typical payload, hydrogen filled, APRS tracking, and lately the FAA in Arizona, since we're near, the group is near Phoenix airspace, they're requiring mode C transponders now. I don't know if you guys have run into that yet. Well, get ready. So Jack, every flight we actually call ATC and let them know what we're doing. And then lately the response has been, you guys should really start flying mode C. So mode C is an aircraft transmitter. It squawks at a certain code, and also its altitude. So they'll see our balloon on their screen. The Phoenix Center will. Then also a crossband repeater. This comes in real handy when the balloon is at altitude and we're trying to track it. And most of these launches are done in the Arizona desert. There's no other repeaters around, or they're scratchy, not reliable. Both the track team and the base team can't really talk to each other. So soon after the balloon gets to altitude, the crossband repeater comes in and provides very, very reliable communication. It's 2 ASDN radios that are kind of hooked back to back, UHF in and VHF out. Runs on alkaline batteries. And also paramount in the whole thing is our student payloads. So Jack launches payloads from high school groups and also college groups. And in particular, the University of Texas, the one I'm involved with, he's launched 3 payloads. And we'll talk about those kind of payloads involving my program called Snapsat. So before I met Jack, though, I was actually involved with a high school group in San Diego. And that group, we were using hydrogen, but the last launch was, using helium, but now using hydrogen. their typical payload, the one I was actually directly involved with the high school, they use a Trackwino. So have you guys ever heard of the Trackwino? So it's an Arduino-based board that you can buy. And you look it up on the internet, called Trackwino. And built into it is an actual Arduino CPU plus a Venus GPS. So we don't fly the GPS that was mentioned by Bill. We actually fly the Venus GPS. It's available through SparkFun, and it doesn't have the 40,000 foot limit in it. We've tracked all the way past 100,000 feet with the Venus. So for the newcomers, there's a federal regulation that these certain GPSs must shut down at 40,000 and above. It gets to be kind of a possible way somebody could build a bad thing with it. And so you have to be careful. You can't just fly any GPS for the people who are going to try this in the future or who haven't done it before. The one that Bill mentioned, and also the Venus from SparkFun is the Venus one is our favorite. We're also running a UHF transmitter, 20 milliwatts. So this was a Chinese knockoff of well, it's actually, the model was called ACP220. It was a 12 volt, 20 milliwatt. It actually was a transceiver. The thing that attracted it to us to that particular model was its forward error correction capability already built in. And so it was on 434 megahertz in a ham band, only 20 milliwatts, and later on I'll show you some pictures we got from almost burst from that small transmitter. The payload also collected telemetry data like temperature inside, temperature outside, barometric pressure, GPS location, and also put an IMU on board, accelerometer and magnetometer. And we actually have data that was parsed from that, and also pictures. All this stuff came through the 20 milliwatt transmitter. Max altitude of the particular flight was about 100,000 feet. So it looked like this. That's the complete payload there. That is the ACP220 UHF transmitter. Oops, sorry about that. The Arduino board below, the magnetometer, accelerometer, barometric pressure, and some inversion logic in there. So our GPS unit, we had to invert the signals, get into the Arduino. There's another shot of it. On its side, there's a power module on top. And so this is all encased inside a styrofoam cooler. So there was one question before the meeting, well, what do you put the stuff in? Styrofoam cooler was our choice. Okay, so from altitude, with the 20 milliwatt transmitter, this is an actual live picture from the payload I just showed you. So using the Arduino payload and that 20 milliwatt ACP220 transmitter and a 7-element Yagi, I was able to get this picture. This is over the San Diego desert area, and this is the Salton Sea. So if you were to fly into San Diego, you would see this on your approach from an airplane. So this is Imperial County, and that is the Salton Sea. So that's going to be kind of a significant item on the next slide, because we saw pretty much where the payload landed before it landed, because it actually, our prediction software, we were just a little bit off on the landing, and we had to go fetch it. So we made a perfect splashdown landing. We're all looking at it. It landed out there somewhere in the Salton Sea. And we were able to track this overnight and know where its position was, because none of us brought a canoe. We thought a Jeep, a couple 4x4s would do the trick that day. We didn't think we were going aquatic. So we missed our landing zone probably about a couple miles, and we had a nice splashdown. And so that's the actual student teacher, physics teacher, and I had a kayak and a 4x4, and we all trucked out there the next morning. 7 in the morning, we were on site, and he paddled out there and got the balloon payload. So that's what it looked like. And then I mentioned the IMU data. So we post-processed the IMU data from that payload, and we got some pretty interesting pictures from, or actually this is the actual data from the payload as being played back. It uses a Python script, and you will see, you'll not be able to see it. Why aren't you able to see that? It's playing on my screen, but not your screen. Oh well. Let's see if I can just break for a second here. I guess PowerPoint's not being very fair to me right now.
Is it showing up on your preview screen?
It sure is. It's showing up on Cleaver, but I won't.
Go to the next slide then, and maybe it'll show.
The mouse has just become inoperative. Huh.
Oh.
Mouse is on the other screen.
Oh, yeah, you've got
Oh,
the
we
mouse
can
there.
see it. Okay, but I can't see it over here. This is interesting. Will allow me to go to the next screen?
Hit escape.
I'm hit escape. And all right, we'll have to wait for a second here until I get this restored. Can you see?
Well, welcome to the Microsoft PowerPoint error.
Let's see, maybe I can get it back by doing this. Let's see.
There you go.
Okay. No problem. If I could just somehow get out of here. No, it's taking me back.
The worst thing I saw was a Bill Gates demo of his new Windows operating system, and he got the blue screen of death.
Yeah.
Deserved.
All right, maybe this will do it.
If I throw a comment in on the
Might have
water
to-
landing,
You might have to drag it over to the
we had
other.
one last spring, a
I
STEM
can't,
student
that's
and his father
totally,
put a unit up and used our
There we go.
local clubs.
Oh, there you go.
They invested pretty good. They found, it was pretty early for Lake Michigan recovery, but they found somebody in the harbor that took them out and they recovered the payload. And they always figure that's easier than swamps and retreat.
Yeah.
So I'm going to play this over again. A little mishap with Microsoft, of course. It's
So
never
the
happened
IMU
before.
stands for, I'm sorry.
Which one?
IMU, that acronym.
Integrated.
Inertial.
Yes, thank you. Inertial measurement unit.
Oh, okay.
There we go. So these are pictures. This is actually post-processed data from the payload. You can see the balloon spinning here. Its direction. And so this is kind of neat that the students that kind of analyzed this data and figured out where it was.
I have a quick question.
Yeah.
So that part of that is a magnetometer sensor, and in my experience with like SparkFun style IMUs, you have to do a lot of calibration work with them.
Yes, we did do calibration work.
Is there any concern that when you get up to altitude, you're in sort of a different environment with the magnetometer, and maybe the data is not as valid as it could be because the magnetic fields are a little bit weaker or something like that?
That's a good point. I don't think the students analyzed it to that point. In fact, we never even thought of it. We calibrated with due north on the ground, so this is a SparkFun device. And so we followed the SparkFun directions, pointed it north, and then we made sure that when we played the script back, we had north-facing data. So at least when it left the ground, it was calibrated.
Okay.
That's as much data as I can give you.
Thank you.
Did somebody else have a question?
What kind of camera did they use when they took that shot you had 4 or 5 slides ago? Did they have a GoPro on board, or was it just one of those little bitty?
It was another SparkFun camera.
SparkFun?
It was a JPEG camera that we bought for $49 from SparkFun.
Okay.
And so that,
It's got like a little bitty ribbon and it's a little bitty square?
yeah, a little bit square.
Yeah. Okay.
let's see if I can slide this over.
So what was your data rate to the ground?
Data rate to the ground was 4,800. So the baud rate of the unit was 9,600, but the data rate to the ground was 4,800. So it took us about 2 minutes to get a JPEG picture down from that payload.
What transponder did you use?
On that particular, you know, I didn't write the transponder down that Jack is using. Well, we could send him an email message. So W7JLC from Arizona Airspace. If you emailed him that question, he'll tell you. Yes.
That aerial picture that you showed, were you actually seeing the curvature of the Earth, or was that?
Yeah, that was the curvature of the Earth. That picture was actually taken near burst.
What was the altitude?
That one was about 98,000 feet.
Oh, wow.
So,
Gene,
yeah.
did you format that JPEG picture to get the data? How did you do the handshaking with it, or did you just?
Okay, so what I did was I actually invented my own little protocol. Let me get the presentation back. If it'll come back. Oh, wow, this thing is... Will it come back? Oh, there it is. I'm very sorry for this. So this JPEG picture, what I did was, I'll get to it in a second. The first thing that the camera itself actually outputs a JPEG picture, all right? And then we stored that picture to the SD card on board. The file name of that JPEG was then handed to the transmitter task on board the Arduino. And so that was his handshake, nearly the file name. So they would re-access the SD card and start transmitting it. So we'd take it byte by byte. They just start chunking bytes one at a time, and I buffered it into 128 at a time. So I fill a buffer up of 128 bytes, and then tell the transmitter to send it. The receiving side knew every 128 you're going to have data, and to go ahead and start writing that data to disk. The trick was you had to escape the data. And so it's an ASCII type transmitter. It wasn't, you couldn't transmit over RS-232 characters like 00 or escape or the commands that would actually stop ASCII transmission, like break or something like that. So you had to escape those, there's about 8 characters you have to escape. So that was in the protocol too. So just FYI, if you ever try to transmit an ASCII picture, you have to escape the data. So that's the only little artifact I had in there. The protocol actually figured out if you lost transmission or had a block or something like that, it would I had sync characters in there, and it would try to sync up. It wasn't very verbose, but it was verbose enough to get a picture from pretty near burst, about 98,000 or so. That was pretty exciting when I saw that picture. Did you have a question?
I had a comment that, yeah, it's very cool to be able to get pictures in real time from the flight. But what, at the University of Colorado, what the students do is fly a small Canon pocket-sized camera, and you can hack the Canon cameras to set them up to take pictures every 2 minutes. And all of their payloads have these cameras, and they load to an SD card, and they get marvelous pictures all the way up and all the way down. And then you can also fly a GoPro. It's a little more expensive if you use it, but the GoPro with a little bit of thermal protection on it and extra battery, you can take pictures all the way up and all the way down. It's pretty neat.
So the next, go ahead.
Question. Now, when you're transmitting, are you transmitting that digitally, or are you going from digital to analog and then analog back to digital?
So the ACP20 had a serial input, so we would transmit our serial data to the transmitter. It's a $29 unit, by the way, $29 20 milliwatt. So you transmit serial data to the transmitter, and then it would take care of the overall over-the-air protocol. So the ACP had its own little built-in how to get it over the air. And so it wouldn't go, you would not go like from analog to digital like an APRS. You go straight serial data into it. You transmit it 9600 baud to the transmitter, and then over the air, it would be 4800 baud. So that answer it? Mm-hmm. All right, so the other project I work with, how much time do I got left? Okay, 6 minutes? Okay, is the University of Texas, and this is a project that I kind of started with. I work for Qualcomm as a software engineer, and I've become very interested in our own applications processor. So I coined this project SnapSat. So its goal was to actually take one of Qualcomm's SnapSat processors in your phone and actually launch it into space on a CubeSat. So the payload was based on Android, very power efficient, because our phones inherently have that already built into it. So I pretty much borrowed all that logic. And then we also experimented with Wi-Fi. So probably something that this group here might be the most interested in is the data we did with Wi-Fi. We actually used the broadband Hamnet. Now it's kind of classified as Arden. It was a project fork, but it was started as broadband Hamnet. So these are the students actually doing the checkout. And this is a gentleman, Steve, from Arizona Near Space, doing some of the flight planning. As we're doing all the, we just landed, and we're in our labs there in Phoenix trying to do the last minute checkout of their payload. Some more checkout. They actually had to do some last minute soldering, and she learned fast. Very fast learner. Never soldered in her life, and she's making all these last minute solder connections. Pretty proud of her. This is a predicted balloon path. So we use prediction software that we can actually predict about within 5 miles of where these balloons land. So we take as input parameters the kind of balloon you're flying, the gas that's in the balloon, the weight of the payload, the winds and loft forecast from the airlines, or actually from the FAA. And we can predict about where it's going to burst and where it's going to land. And so this is where we deploy our chase teams. This is set up with proper grounding for hydrogen. The way the balloons are actually tethered together, the payloads. And so there's several payloads that actually fly up all at once. It's not just one. We're able to get many experiments up all at once. This is data from the actual payload at 92,000 feet using broadband Hamnet. And so this is the ground station receiving the payload at -88, which is not a bad signal. We're getting a 94 noise floor on the ground. And this is a custom ground station that I put together using Windows. And so this is telling us what time it is. This is the payload telling us what time it is, latitude, longitude. Its altitude at this point is 92,000. And here's some just a running display of the data that's coming across. In this case, it's GPS data. Now the other thing is let's log on to the payload since we have a great connection. So broadband Hamnet allows you to actually go ahead and connect to another node. And I just connected to our payload. So this is the payload looking at us. So the payload actually saw a -83 signal and a -92 noise floor. It's been often commented that, you're going to see a lot of Wi-Fi signals up there. The interference level is too high. And I said, well, let's just see. And so it really wasn't that bad. Given that the inherent nominal noise floor of these units are -95 at 20 megahertz wide, we're only 3 dB off the actual floor. So it wasn't all that noisy. And we had a 9 dB spread and a margin, which that's pretty tight, but I was just thrilled to actually see connectivity at 92,000 feet using 2.4 gigahertz and Wi-Fi. And so I'm going to explore this further. Pardon me?
Did you collect some SIDs from up there? Some network names from up there?
I didn't see any SIDs.
No.
Nothing. And interesting, so when you landing into San Diego, I have this Android application called Wi-Fi Analyzer. If you guys have heard of it, it's a free download. You can all see all the SIDs in your area with the different SSIs, or SSIDs, and also the signal strengths. In landing, I'm not seeing a lot of activity, 10,000, 15,000. It seems like it starts lighting up around 7,000 feet. All of a sudden, I'm seeing 15 to 20 SSIDs on my phone from the airplane. I happened to get a window seat that particular flight. And so that's pretty good. I think that's pretty interesting that most of these Wi-Fi signals are terrestrial. And my just experimental data on the window of an airplane, about 7,000 feet, we start losing those. And when we get up to 92,000 feet, we're not seeing anything. So I think I'm gonna keep exploring it. We're gonna put more stuff out there. We're getting nice pictures from the payload. And I'd like to get actually live streaming video someday from the payload. That's really where I'm going with this. There's the recovery, University of Texas. That was the payload that they flew, camera. And this is the crossband repeater. And you can see how they're all tethered together. Each payload has a lamp thread that goes through it. A threaded rod that came from a lamp. And so they drill holes on each end and put a marine shackle on each end. And that's how we tether all the payloads together, so we can have many students flying on the same flight. There's some post data from the UT flight. We found we had an ascent rate of about 1,000 foot per minute, and we reached a maximum altitude of 97,000 feet. And this is a real picture from the payload that we got. Stunning. I mean, you look out there and you see empty space. You start seeing a slight curvature of the Earth on the end of our atmosphere. And this is kind of what keeps me going, is that we're so small. When you look at these payloads that get up there, and within an hour or two, you're sitting in the edge of space, staring out into space. Kind of, for me, gives me a calibrated feeling.
What's the total flight time for 97,000 feet?
About 3 hours. It takes about an hour, a little bit over an hour and a half to get up, and the remainder of the time to come down. So we fly static parachutes. So let's see, there's the parachute right there. This is for the newcomers. And so the parachute goes up with it. It's statically connected, and on the way up, it doesn't open because you're going reverse on the parachute. But as the balloon bursts and starts coming down, it catches air, opens up, and it floats most of the time gently to ground. On this particular flight, just before it hit, I was looking at a descent rate about 1 foot per minute. It just gently touched down. And for the last slide, I don't know if I'm going to post this on the internet. Probably, will this get up on the internet? I put some contact information for Jack's group.
Yeah, that's great.
All right, so I apologize for the PowerPoint stuff there, but I hope you guys got some data out of this. Yeah, go ahead.
Could you tell us more about that Mode C transponder?
We're going to have to talk to Jack on that. So I didn't bring that data from Mode C with me.
Do you have any idea of roughly how expensive they are?
I think it's over $1,000. Yeah, it was a big chunk.
How heavy they are? Yeah.
I don't know. I don't have the specs on it, but it's not heavy enough to cause the flight to. We're able to get it up there. What was your question on the frequency?
The guy last week said it's about 1090 is the megahertz.
I was going to say around a gigahertz, just over that.
C3C transmits on 1090, receives on 1030.
Thank you. Yeah, about just over a gigahertz. And so it didn't seem to interfere with the 2-point gig stuff. Didn't seem to interfere with the Mode C on this flight. Yes.
Is that above a certain weight that you need to transport?
Well, each payload we can't launch more than 6 pounds all together. That's by the FAA rules. So the whole aggregate is under 6 pounds.
Actually, it's 12 pounds, but each payload, individual payload can't exceed 6 pounds. You could have 12 one-pound payloads.
But the question is, what triggers the requirement for the Mode C transponder? What payload size or weight triggers that requirement?
Yeah, 101 states what Bill just said.
It's not in 101. That must be a local requirement
think it's getting to be local, because Jack's done so many flights in the area. But Jack said this is probably be coming to our doorstep real fast.
So theoretically, HICO payloads could require it in some areas.
You know, I'm not, since this seems to, so this is the only group. So we launched in San Diego, and we're not, when we call in our flight plan, we're not required to fly no seat. But Jack's group, the Phoenix Center is requiring him to put this on there. You want to see it. So whether this is going to be an isolated case or not, but it doesn't, I think this may be catching on.
Well, EOSS guys, do you have any, you are closely in touch with the FAA better.
I'm going to say that most of our flights are not exempt. We fly with an FAA waiver. We have to go in with a flight plan a week out.
Yeah.
We have to call an hour before launch. We have to call launch. We have to call burst. And we fly no transponder. However, we created a web page for them. And our data comes down real time and shows up on the web page that they can see that the data isn't just lat long. It's VORs, if you know what a VOR is, visible. It's a navigation aid for everyone. So we give them 2 VORs, we give them range and bearing for both of them.
Yeah, VHF Omni Range, EOR. That's what it stands for. And I know we were calling in, it's pretty much the same thing you were doing. And so maybe Jack, do you know Jack? All right, maybe Jack and you can have a conversation.
I would.
I think it's important to Blue in
That's
general.
the first I've heard that is being, it was requirement by them.
Yeah, they're saying mode C. So it was kind of a large expense for the group to fly that. Okay, I'm going to pass it on then.
Just to